Okay.
Center screen. Whichever one is center screen.
This one, I would prefer this one.
Okay.
You're basically able to send any source you want to the center screen.
Okay.
So if you just select it here,
And
then-
if you could come just before 4 o'clock, I would appreciate that, guys.
no problem.
It's already. Guys, good afternoon. I'm sorry for the delay because the technicians were late. So I don't really know what I can do. So as I said in the email, today, last Wednesday, I started talking about maximum likelihood estimation. So today, not just today, but today and tomorrow, I'm going to do examples on maximum ML estimation, right? Because you in the exam you will get at least 2 questions. The exam in June or May or June of this year, you will get at least 2 questions that involve use of ML estimation, right? So it's really important that you do get this right. Yeah. Okay. Remember, there are. You may remember from last week that I talked about 3 different cases. So let me just remind you. Case A was that where the parameter case A was where the parameter theta was a scalar parameter. So examples could be like the exponential distribution has, or the geometric distribution. All right, these are two examples of distributions that have only one parameter of interest, right? Case B is where the parameter theta has two components, theta 1 and theta 2. So examples could include the normal distribution or the gamma distribution or the beta distribution. Each of these distributions has 2 parameters each. And case C is where parameter of interest theta has more than a k number of components, right? So it has k parameters. So in this one example is where the linear regression model, the linear regression model is an example of a model where you have any number of parameters that are not known, right? I started with case A, so let me put this over here, guys. I did a couple of examples on case A, but I must tell you you can get a variety of different examples in case A, or even case B also, because let me explain a situation where you should look at let me guys sit down because I don't feel very well today. I hope you can forgive me for not standing up. I'm not feeling well. Sorry. All right. Now, let me do an example. The two approaches that I looked at last week, they use what is known as the standard approach. Sorry, guys. This is known as the standard for finding MLEs. The standard approach is what I talked about last week, although I did not call the name standard. It's basically, it involves you write down L of theta, take log of L of theta, then solve this equation, right? And if all right, this is what is known as the standard approach for finding the MLEs. So you write down the likelihood function, take the log likelihood, you differentiate the log likelihood with respect to the parameter, set it equal to 0, and if theta equal to theta hat is the root of this equation, then make sure that this is negative. Now, this standard approach does not always work. It doesn't always work for every problem. Now, that's why we need other approaches. You need other approaches for finding the MLEs, right? So that's what I'm going to talk about today, guys. Can you see this, guys? Let me see. Okay. the standard approach does not always find the maximum likelihood estimators, right? Now let me give you an example. Let me give you an example where the standard approach does not work. Okay. Suppose okay, consider this example, guys, where you have a random sample from the uniform distribution on the interval 0 to theta, and we want to find the MLE of theta. Now, if you have to use the standard approach, first of all, we need to write down the likelihood function, which is the product of the density functions. Now, what's the density of the uniform, guys? You remember? Yes, no? Do you guys remember the density of the uniform? Yeah? Guys, you should have better memory than me, guys. It's 1 over theta, right? Or it's 1 over b minus a. So this is 1 divided by... Now, then take the log. Log of L theta is the log of this, which is then you differentiate the log with respect to theta. Okay, and you set this equal to 0. If you set this to 0, what is the root? If n over minus n over theta equal to 0, theta can only be the only possible roots of this equation are theta equal to either plus or minus infinity. Do you guys follow or no? Yeah? So that means the standard approach, this is the standard approach. The standard approach for finding the MLE of theta does not work because you are getting a solution for theta which is undefined. All right? Excuse me, guys. All right, so you're getting a solution for theta which is undefined, plus or minus infinity. Okay. Now in this case, what do you think went wrong here, guys? Why do you think we are getting this weird answer? Huh? We are getting this weird answer. I will explain in a minute, guys. We are getting this weird answer because, remember the uniform distribution. The uniform distribution is defined between 0 and theta. right? That means is undefined outside that interval from 0 and theta. Okay, so when you write down the likelihood function, you need to make sure. So that's why I'm going to introduce I will explain this in a minute, guys. I'm gonna introduce an approach. I'm gonna introduce an alternative approach for finding the MLE in cases like this, which I'm gonna refer to as the indicator function approach. So let's look at that example one more time, right? So the likelihood function is the product of the density, but remember the uniform distribution is defined between 0 and theta. So I'm gonna say this following, guys. Have you seen this function before, guys? Yes? No? Did you seen this function before? No? It's known as the indicator function. It's known as the indicator function. What it means is the following. It means that it takes two values. One, if A is true, zero if A is false. And this is the definition of the I function, right? It takes the value 1 if A is true and 0. So what it means in this context is that this is equal to 1 if xi is between 0 and theta, and is equal to 0 otherwise. All right? Because remember, the uniform distribution is defined only when xi is between 0 and theta. So you don't want to define it if it is outside the range. All right? All right? So in this case, this will simplify to this. All right. Now, over the years, I had lots of troubles with student understanding how to simplify products of. So what you have here is a product of indicator functions, and I had problems with students trying to manipulate this. So because of that, I'm going to give you guys some rules. Right? These are not really difficult rules to memorize. So let me give you some rules on how to simplify products of indicator functions. So if you have a product like this, I from 1 to n of this, then that's the same as, sorry guys, it's the same as this, the maximum of the xi's being less than or equal to A. Okay? And if you have if you have something like this, n, if you have a product like this, that's the same as excuse me. Okay. And one more rule. All right, these are sorry guys, I'm crossing on something. These are rules I would like you to remember for the rest of this course. All right, that is, what these rules tell you is how to simplify products of indicator functions. All right, so this equal to this and so on. So right, if you apply these rules to this one, what do you get, guys? You will get what? What you have here is a product of indicator functions. Following these rules, what would this simplify to? Huh? Don't look at me, guys. All right, do you see this? Can you see that applying this last rule, this one, to this product, this simplifies this to this? Can you see this, guys, or no? Yes? Yeah? Okay. All right, so this is the simplified form of the likelihood function. Now, we are not done yet, so let me put this over here. Now, the next step of the indicator function approach is to draw a picture. I don't have a pen. So what I'm going to do is on the y-axis I'm going to put L of theta. On the x-axis I'm going to put theta. Now what I'm going to draw here is the function, this function here. How do you think, if I draw this function on this graph, on this axis, how do you think it will look like, guys? suppose this corresponds to the max of xi, right? Your graph will look like this on this side, and it will be zero, flat zero on this side. Can you see why? Don't just say yes, but do you guys understand why the graph of this function versus theta should look like this? Yes or no? Because remember, this is an indicator function, means that it takes the value 1 when theta is greater than or equal to the max of xi. That is, if you are on this side, it takes the value 1. So it's 1 times 1 divided by theta n, which is a decreasing function of theta. Now, if theta on this side, that is, if theta is less than the max of xi, then this condition is no longer satisfied. All right, and therefore this whole function will be 0. So it will be flat 0 on this side, and it will be a decreasing function on this side. Right? Now the question is, remember the principle of maximum likelihood estimation is to find the value of theta for which the likelihood is largest. The likelihood L of theta is largest at this point, all right? Okay, and the corresponding value of theta, corresponding to the largest likelihood is max of xi. So the MLE of theta is equal to max of xi. Is that clear, guys, or not? Do I make any sense, guys? Huh? No? Yes? Right, so what I have done is to write down the likelihood function, right, and plot the likelihood function versus the parameter theta, and find the largest point of the graph, because remember the principle of MLE is the value of theta for which the graph attains the largest value. The graph here attains the largest value over here. This is the largest possible value of the graph, and the corresponding theta value is this, and therefore theta hat is this. Yeah? You alright, guys, or no? Yeah? Okay, guys. So this is not, this approach, which I illustrated through an example, is known as the indicator function approach. Now, let me formalize it. Oh, here we are. Let me try to make it more formal, okay, so that so here we are. This is the indicator sorry, guys. So Right. The first step is to write down the likelihood function in terms of indicator functions, right? That's the first step. Second step is to simplify the likelihood function as much as possible using the rules. When I say rules, I mean these ones here. These are the rules. These three are the rules. Okay? Third step, plot is to plot the likelihood function versus theta. Fourth step, is to find the largest point of the likelihood function, like I did. This is the largest point. Can you guys hear? This is the largest point of the likelihood, right? Finally, step 5, the MLA is the corresponding theta value. So this is a formal description of the indicator function approach. Now, as I said, the standard approach doesn't work all the time. And if it doesn't work, you can use the indicator function approach. If it does work, you will need to use the indicator function approach, right? Okay. So let me do one more example on the use of the indicator function approach, right? Maybe it's not so clear to some of you. Some of you seem lost. I don't know. Right. Let's look at another example where the standard approach, so this is exercise 28 is from this thing here that I gave you guys a while ago. Yeah. Exercise 28. You have okay, guys. Sorry, guys. So you have a random sample from a uniform distribution from this to this. Now I'm going to write down the likelihood function. I'm going to first use the standard approach. The standard approach is the product of. Now, what's the density function of this, guys? Just help me, guys, with this. What's the density function of this? Huh? Yes. It's 1, of course. So the product of 1 is 1. Take the log of L theta is 0. Okay. So what is theta? Log of L theta is 0. So theta doesn't make sense, right? Is 0 for so the standard approach doesn't work. So I'm going to use the indicator function approach. Now use the all right, the first step sorry guys, is the indicator function which says you see what I've done, guys. I'm saying that is 1 times the indicator function, right? That's saying that every xi must be between theta minus a half and theta plus a half, right? So what you have is now, do you know the rules? Let me remind you the rules, guys. These are the rules. Now, if you apply these rules, what would this simplify to? It will simplify to the following. It will oh, sorry. What did I do? Oh, that's okay. That's magic. It's some kind of magic, I guess. Maybe I should stand up. Okay. All right, this will simplify. Oh, let's come back. right? You see, so I have used this rule here, guys, to simplify this product to this. Yeah, you're with me? All right, now all right, I made some changing around, and finally Jesus, sorry. All right, this is what you get after simplification. All right, this is the simplest that you can simplify to. All right, so the next step, guys, is to plot theta on the x-axis L of theta on the y-axis. Now, if I plot this, how do you think it will look like? Come on, guys. You should know this, guys. How do you think it will look like if I draw a graph of it? Suppose you have 2 points. All right, suppose this one is the okay, and this one is the all right. Now the graph will look like exactly, guys. So it will be a straight line between these 2 points, right? Yeah, and outside that range it will be 0. You guys see this or not? Yeah? It's simple, right? The graph of the likelihood is... Now, let's answer this question. Where is the largest value of this graph? Or what's the largest point of this graph? Any point between the 2 points, right? Any points between these two gives the largest point of the graph, all right? So the answer to the question is that MLE of theta belongs to MLE of theta belongs to the interval from the max of xi minus a half to the min of xi plus a half. So there's no unique solution to the MLE. All right? I mean, in this case, there are uncountably infinite solutions for the MLE, right? Yeah? Is that clear, guys, or not? You okay? All right, guys. I will stop now, but I will do more examples when I see you guys tomorrow. Or I will see you later today from 5 to 6 for the example class. Oh, yeah.
Next lecture, at the beginning, I just give a speech.
Okay. Yeah, that's fine. Yeah. Yeah.
Anyway, I have to get better soon.
Okay.
Do you hear? I said bless you in the lecture, but I didn't know if you heard it.
Sorry, I've been having a bad flu all of this week. So I don't know.
Well, thank you for still being in the lecture.
Okay. Thank you. Thank you. Bye.